This conference will now be recorded. This conference will now be recorded.
Very good evening, students. So, as we had promised, we'll learn today Kirchhoff's law. So, let me first of all tell you why do we need Kirchhoff's law and what is all about this Kirchhoff's law. Okay. So, see, Kirchhoff's law is actually used to find out current or voltage drops across certain branch or sometime equivalent resistance also we will be able to find out through Kirchhoff's law if required. See, generally when we have a circuit, and we have to find out current through that, suppose I have multiple resistances. Suppose I can actually use this kind of network, and maybe battery is connected at these two ends. So what will be the current through the circuit or current through some particular resistance? So this we can do using Ohm's law, right? If suppose say this is R1, this is R2, and this is R3. Look, these two are in series, which is parallel to R1. So I can find out current according to that. Okay. Again, I may have very complicated circuit where I may not be able to find out the equivalent resistance of the circuit. So in that case, I may not be able to find out which one is parallel, which one is series. So in those cases, we use Kirchhoff's law to find out current and voltage drop across certain branch. Okay. So Kirchhoff's law is important to analyze complicated electrical network or electric circuits. Okay, so first of all, I will let you know few terms. Okay, some terms which we are going to use here. Some terms, then I will come to Kirchhoff's laws. Okay, so first term is electrical network. What is that? The term electric network is used for a complicated system of electrical conductors. See, first term is electrical network. Electrical network. So actually it is a complicated combination of conductors, I can say. Complicated system. It is said complicated system of conductors. That is actually electrical network. Second term we learn junction. So junction, in general, junction you know, but here electrical junction, suppose I have a network like this. Then from here one branch is coming out, then again another branch is coming out like this. Suppose there is a circuit, and maybe from here there is like this. Okay, this is kind of circuit. So what is the junction? Junction is the point where two or more currents are meeting, or two or more currents are going and meeting, suppose this, and it is coming out through this. Okay, so any point in an electrical circuit where two or more conductors are joined. So any point in an electrical circuit where many conductors are meeting. Okay, so this is called junction. Now what is loop or mesh? Loop or mesh. It is actually any closed conducting path in an electrical circuit. Closed conducting path. Closed conducting path. So this is a closed conducting path. And what is a branch? Branch. What is a branch? Branch is a part of electric circuit between two junctions. Circuit or network, electrical circuit between two junctions. Okay, between two junctions. Let us say this is one branch. This particular thing is one branch. So this also may be one branch, because there is one junction here, here another junction. Okay, so junction is a branch. Branch is a part of the network lies between two junctions. Okay, so what we have learned, electrical network, that is complicated system of conductors. Then junction, any point in the circuit, in the electrical circuit where many conductors are meeting. Then loop or mesh, that is closed conducting path. And branch, part of electrical circuit between two junctions. Okay, so these are few terms I need to use while teaching Kirchhoff's law or learning Kirchhoff's law. You need to know these terms. Now come to the point, Kirchhoff's law. So there are two laws, okay, given by Kirchhoff. So Kirchhoff is actually a German physicist. German physicist. Okay, so Kirchhoff is actually German physicist, and he gave two laws or two rules. Okay, one or first rule. See, Kirchhoff's rule has different names. First, Kirchhoff's first law. First law. It has another name, Kirchhoff's current law. Okay, Kirchhoff's current law. Kirchhoff's current law. Second is Kirchhoff's second law. This has three names actually. Kirchhoff's second law or Kirchhoff's voltage law. See, Kirchhoff's current law is abbreviated as KCL, and Kirchhoff's voltage law is abbreviated as KVL, which we are going to discuss. And so there are two rules, and Kirchhoff's voltage law has got another name, Kirchhoff's loop rule, or simply loop rule. Loop rule. Okay, so these are actually two laws. Kirchhoff's first law, which is again known as Kirchhoff's current law, which is abbreviated as KCL, and Kirchhoff's second law, or it is called as Kirchhoff's voltage law, or KVL, Kirchhoff's voltage law, or Kirchhoff's loop rule. So we'll discuss first the first one, Kirchhoff's current law. So what is this law saying? Kirchhoff's current law. It is saying that the sum of all the currents into the junction is zero. Or in other words, what we can say? We can say algebraic sum of the currents at any junction is zero, or sum of the currents entering. So, or sum of the current entering into the junction and coming out of the junction. Sum of the current entering into the junction and okay, so this is not sum, or the okay, sorry, or the sum of the current entering, sum of the current entering into the junction is equal to the sum of the current coming out of the junction or going away from the junction. Okay, what does this mean? See, according to the first statement, sum of the currents. See, here I have got junction J here. See how many currents are going, how many currents are there? I1, I2, I3 and I4. So I can write according to the first statement that the sum of all the currents at any junction will be zero. So I1 plus I2 plus I3 plus I4 must be zero according to this statement. Now according to the second statement, the current entering and going out to a junction can be assigned sign. Okay, suppose the current which are entering into the junction is assigned positive sign, and the one which are coming out of the junction are assigned with negative sign. Okay, negative sign. Then what we can write is, this is also coming out of the junction, so I can write, so according to the second statement, I1 plus I2 must be equal to minus of I3 plus minus of, let me write it here, plus minus of I4 plus minus of I4. Okay, so ultimately what you get, I1 plus I2, that is equal to minus of I3 plus I4. So this is the current which is going out of the junction, and this is the current which is entering into the junction. Now if I take this right hand side towards the left side, then I get the previous formula back. So Kirchhoff's current law has two statements. One is the sum, algebraic sum of all the currents at any junction is 0. And second statement is all the currents, sum of the algebraic sum of the, no, not algebraic, the sum of all the currents entering into the junction will be exactly equal to the sum of the currents coming out of the junction. Okay, all right, so far it is good. Now let us see how do we justify this thing. Like, I'll tell you. So how do I justify this I1 plus I2, that is equal to minus I3 plus I4? Other things I will erase. So how can we justify this, that this happens? And the I mean to say, on which principle this KCL is based on. Okay, so the KCL actually is based on the conservation of electric charge. Look it here. See, this is conservation of electric charge. See, some charges are coming through this conductor and just reaching to the junction. Through this also some charges are coming and reaching to the junction. Okay, but you know, according to conservation of charges, charge cannot accumulate at the junction, right? Charge cannot accumulate at any point in the circuit. Charge cannot get accumulate. Okay, charge cannot get accumulate at any point. Okay, at any point. That's how you get the current in the circuit. So if at any junction the current is charges are getting accumulated, so you will get gradually decaying current. So Kirchhoff's law is based on the charge conservation. Okay, according to this law, see, according to this, no charge can accumulate. Okay, no charge get accumulated at the junction, gets accumulated at the junction. Okay, so that means how much ever charges are coming into or coming towards the junction, the same amount of the charges will go out through this conducting path. Okay, so that means the number of charges are coming towards the junction and the number of charges leaving the junction are the same. So that's how we can say the amount of current entering into the junction and leaving the junction are the same, but we are taking the current direction wise. We are just taking the current positive when entering into the junction and negative when they are leaving the junction. Okay, so charge conservation. So charge conservation says charge cannot get accumulate anywhere. Okay, it will flow. All right, so this is all about Kirchhoff's current law. And in fact, this will be very good when we, like, you will understand better when we do some numerical examples. Now we'll go to the next law, that is Kirchhoff's voltage law. So this is very important, you need to learn it. So Kirchhoff voltage law is saying that this is called also loop rule, Kirchhoff loop rule. So it is saying that algebraic sum of the potential difference in any loop, including those associated EMFs and those resistive elements, must be 0. Or in other words, I'll write in another words, the algebraic sum of EMFs, the algebraic, this is oblique, so the algebraic sum of the EMFs in any closed loop is equal to, so algebraic sum of the EMFs in any closed loop is equal to the voltage drop across various resistive elements. Okay, equal to the sum of products of sum of the products of current and voltage, sorry, current and resistances. Current and resistances. I'll let you know what it is. See, in the first statement mathematically can be expressed like this. Okay, the second statement can be written like this. See, all the EMFs they are in the circuit, their sum will be exactly equal to the IR. So summation of epsilon is equal to summation over IR. Okay, now we'll learn few sign conventions. See, there are few sign conventions here. Sign conventions while calculating sign conventions. So this is having so see, EMF means EMF is actually associated with the battery or the cell used in the circuit. So while summing up these EMFs, we need to be very careful to take the sign of those. Okay, sign of the cells. Like, see, I am showing you here. See, suppose I am choosing a loop. I'll discuss what is the formal way to solve or use this KVL. So while going from, see, the negative terminal to positive terminal or low potential to high potential, if you go like this, then the voltage drop across, or the potential difference between these two plates will be written, say VB minus VA will be positive. Okay, positive. That means, you know, the as if the current is, see, as if current is sent from positive terminal. As if the current is just generated or sent from positive terminal of the battery. Okay, so in that sense, EMF should be positive. Further, you look the second figure. This is first figure. Second figure, you look here. See, so we are going from high potential to low potential, and as if here the current is as if the current is sent from negative terminal. Okay, so in this case, you look VB minus VA, this potential difference or potential drop or EMF of the battery has to be taken as minus. Okay, we'll discuss when we go for an example. That time it will be very clear. Okay, we'll go to the next example. So let us see. First of all, let us see how to proceed with this kind of problem or Kirchhoff's law problem. How to proceed? Okay, I have got some more sign conventions over here. You can see in this case, when the current is flowing from A to B, okay, A to B, if I take voltage drop VB minus VA and going in the same direction, okay, here the convention is okay, so VB minus VA, that means this is at actually low potential, and here it is, this is at higher potential, so that's why we are taking minus IR. In other way also you can take this as positive. Okay, you can take this, we'll see while doing calculation, we'll show you. I can take just IR, okay, and this I can take negative IR also. All right, so that depends all about conventions. In this case it is justified to take negative because, see, I am taking generally this generally will be at high potential, right? Positive term, high potential, at high potential, and there it will be at lower potential. So Vp minus Va is equal to IR, that you have to write negative. But in this case, see Vp minus Va, negative of negative. So the current is in the opposite direction. So negative of negative will be positive. Okay, so these are few things about sign conventions. Sign convention. Okay, we'll go to the example part. How to proceed? See, first of all, look here, A, B, C, D, A. This is a closed loop. So we have found out closed loop. So we have found out closed loop. Now, first of all, what we'll do, we'll denote this battery terminal as high and low. Look what we have done. See here it is high, positive terminal, and negative terminal is low. So this point will be at high potential, this point will be at low potential. Similarly, this point will be at low potential. Since it is negative, this will be high potential. This will be at high potential, this will be at low potential, right? So if we just denote with high, low, all these things, then it will be easy to find out the direction of the current. Okay, so look, in this case, if I have to see sometime, so this is suppose a loop, so closed loop A B C D. So loop A B C D A. This is the loop, closed loop. And say I'll just see, if I suppose go from A to B to C to D, then better to give an arrow like this. Here only one loop is there, but there could be multiple loops also, and then there will be multiple resistance. Okay, so for the loop this here, look what I'll write. First of all, let us say what are the summation, okay, or okay, sum of all the voltage or change in voltage equal to 0. This will write. So here, what will be the Kirchhoff law? Like, what will be the equation for this case? See, I'll take this I as a current which is passing through R1, as well as see, since it is same loop and all are in series, so this current will be passing through all the circuit element. Okay, and what I am going to do, I am writing loop rule. See how to write a loop rule. See, in this case, E1, see, this is high and low. See, how do I take this EMF of the battery? I'll take negative, because as if it is seen, see, in the previous, see what we are taking, potential as negative. Okay, Vp minus Va. So change in the voltage here is negative. See here, I'm sorry, here, change in the voltage is negative here when I'm going positive to negative terminal. So here it is happening. Look, high to low we are going. So change in the voltage across this is minus E1. What is the change in the voltage in this case? Say high to low. So again it will be minus I R1. So here low to high. Okay, low to high, it will be positive. It will be positive. And what about here? See, low to high to low. In this case also, it will be minus I R2. Okay, equal to 0. This is the loop rule. Okay, so now I can actually arrange. See, if I have to find out current, so I'll write minus of I is equal to R1 plus R2, and here it will be plus E2 minus E1 is equal to 0. Now see, I can find out I is equal to E2 minus E1 divided by R1 plus R2, and with a negative sign. With a negative sign. So I can write E1 minus E2 divided by R1 plus R2. Okay, so this will be the current in the circuit if I would like to find out that. Now I'll take a practical example for this. So this is a practical example. So here we have to find out current through each branch. See, I have current through this branch, this branch, this branch, this branch, and this branch as well. So I have to find out the current through each branch. I have to find out that. So for that, you know what we can do? So here also you can actually denote high, low, etc. If you like, we can write a high, low, etc. So in this case, I'll just denote say what are highs, high. So this is low, this is high, then this is again high, this is low, this is low, this is high, this is again high, this side it is low. Okay, this is also low, this is high. This is low, so this will be low and this will be high point. And this side it will be low again. So if I denote high, low, thereafter what we need to do? We need to actually write. See, there are two loops in this case. I'll just go from A to B to H to A, sorry, H to F, sorry, here A to B, B to E, E to F, and then A. So loop, see, for the loop A, B, E, F. So for this loop, what is the Kirchhoff's law? Like according to Kirchhoff's law, we'll get one equation, and in this also we'll get another equation. Then I have to solve for the currents. Let us suppose a current I1 is flowing out from this battery, and it will flow all the way, see, up to here, and it will be getting into branch. So this is I1. I1 will actually come up to here, and this will be here. The current will be divided into two. One is C, one is R3. So this way there will be two currents. So one is I plus. Okay, so as you understand, I can, okay, let me So this I1 itself is actually getting divided into two parts, let us say. So from the loop 1, what we can write for the loop 1? See, for the loop 1, here I'm going from high to low potential, and see here low to high potential. So EMF will be positive here, then plus. See here drop across. See, I'm just supposing current I1 is passing through 4 ohm, but as you said, so it will be minus I1 into 2. Then see, this is actually positive for voltage, and this one, see, I'm going from high to low. This will give you again, this will be I1 this way, and say here will be actually, see, when I2, one part is going this way, another two parts must be here. Okay, so I3 is passing through this way, say. So for the first loop we have got, so I have started from here, see, if then battery I have got, this is positive, this current, so this is 4I, okay, I'm sorry, this will be minus 4 into I, this is 4 actually, and see, this voltage is positive and this is again negative, this will be 2I1. Okay, so what is the equation ultimate what we are getting? This is minus 6 I1, this is actually plus 6 voltage. So this is the one, if we simplify a bit, then we'll get actually this current to be 1 ampere. So I1 we are getting from the loop 1 itself. Now look, there is another formula, see, not a formula, this is I1 is equal to I2 plus I3. Okay, so we have got from loop 1, we have got what is the current I1. Loop 2, so loop 2 is the one that is BCDH. BCDH. This is it. So loop, for loop BCD, BCDF, sorry, EF. For this loop, let us write the Kirchhoff law, KVL. See, so look what we can write for this. See here, low to high we are going, so we can write 2I2 minus. Here high to low we are going, See, like this, high to low, that means we'll write minus 6 volt. Then here we are going low to high, so minus 4i, minus 4i2, this is i2, minus 4i2, and here it is high to low again, this will be again 4 volt is equal to 0. So this is also here 6i2, and this is actually 10 volt. Ten volt. This is say 10 volt. Okay, so we can write from here. Sorry, this is I2. I'm sorry, this is actually or I2 is equal to 10 by 6, then it is 5 by 3. So we have got current I2 is equal to 5 by 3. Okay, current I2 is equal to 5 by 3. Oh, I'm sorry, this just a minute. Yes, so current I2 is equal to 5 by 3. We need to check whether we have done some direction mistake. Okay, I'll just clean everything. Let me do it here. So this was high, this is low, this is also high to low here, and this is low to high. Okay, here low to high, this is high actually. Okay, so this is high to low, this is low to high, and then this is high, this is low. Okay, so I have taken, see, current I2 is passing through this way and I3 is passing through this way. So I1, total I1 will be I2 plus I3. Okay, now see, for loop B, C, D, E, and again B, this loop, for loop this we can write, see, I start from B, so current will be, see, here I'm going low to high, so it will be actually positive I2, 2I2. Here, so this battery, see, we're going high to low, 6. Then here, at this particular branch, see, I'm going from low to high, so the current will be again, see, voltage drop will be here, voltage drop will be low to high, so it will be positive actually, positive 4I2. And then it is going from high to low, so it will be positive volt. High to low, that means negative voltage again, like this. So we get 6I2 to 4. Okay, No, I think I'm just doing a small mistake related to sign. Let me check once. So minus 2, we have done sign mistake. Okay, so this will happen when we, okay, so we may actually just go in other direction also. Okay, let us go with this direction. So what we have done, see the current I have taken I1 here, okay, and this way it is coming, and I am taking another current I2 here. It is starting from here and it is going all the way here, okay, and this will combine with I1 here. So this will combine with I1. So this branch particularly will have I1 plus I2, okay, current, and then again it will be here I2 this way and I1 this way. Okay, in that way also we can go with. That means we start with ED, then CBE. With this loop, so what we can do? So in this case, see, this is, we're going this way. So negative to positive, that means 6 volt. So from here, see I2 is going this way. So this is high, this is high, this is high, so this is low. So this will be again positive, say. So 2I2. Okay, again, see here it is also positive, going from low to high battery. Okay, so, and this one, see from high, see we have taken this is low, so low to high actually this way. In this way current is C. This will be also positive. So this will be 4I2 again. This is 0. That means, you know, this is 6I2. Okay, let me check with this 2I2 again. 2I2 I have taken this way. Oh, I have to, yes, I'm going from all the way E to ED. So this is 4I2, all right. Then it is going like this, polar positive. Is equal to minus 10. So I2 will be equal to minus 10 by 6. That means minus 5 by 3. Okay. So this is how we have to solve numerical problems on Kirchhoff's law. What we'll do in the next class, we'll take various type of numerical problems on this topic. So thank you for your patience. Bye for today.